Hello, calculus fans. Okay, so if you were to take the graph of y equals cosine x and graph it, there's going to be a local maximum near x equals 1. Now you may want to take your calculator and go ahead and see this. You don't have to zoom in real far. It's going to be near x equals 1, but it's not going to be exactly at x equals 1. Now what we want to do is try to use Newton's method to estimate the x-coordinate of this point, where this local maximum is. And we'll do it correct to 3 decimal places. Now local extrema occur at critical points. So remember, that's where the derivative is 0 or doesn't exist. So if we compute the derivative of this function, we have to use the product rule, and this is what we'll get. So we'll get y prime is equal to negative x sine x plus cosine x. And that's just using the product rule in the original function. Now we want a critical point, so we're going to set this equal to 0. And so this is the equation that we want to solve. That is, we want to try to find a root of this equation. Now this is not something that we can do algebraically, so we go ahead and use Newton's method. So I'm going to create a new function. I'll call it g of x equals negative x sine x plus cosine x. And we're going to use Newton's method on this function. I don't want to use Newton's method on the original function. That would be finding out where the original function hits the horizontal axis. I'm not interested in that. I'm interested in knowing where the derivative of the original function is 0. So that's why we're going to start with g of x equals negative x sine x plus cosine x and use Newton's method on that. Now if we're going to use Newton's method on g of x, we have to compute its derivative. So we'll use the product rule on that also. So we'll get negative x cosine x minus sine x, and then another minus sine x. So the first sine x is part of the product rule. The second sine x comes from differentiating cosine x. And now we'll get negative x cosine x minus 2 sine x if we clean that up. Now I'd like to plug this into the formula for Newton's method. We'll get x sub n plus 1 is equal to x sub n minus g of xn over g prime of xn. That's the iterative formula for Newton's method. Now let's plug in g of x and g prime of x. And if we do, then we get this formula. Now remember that the problem statement said that there's a local maximum near x equals 1. So I'd like to go ahead and use x sub 1 equals 1 as our initial guess and then iterate using this formula. Now if we do that, Newton's method will spit out values that look like this. So if you plug 1 into that formula, you would get 0.865. And you plug that back into the formula and you get x3 equals 0.860. If you do one more, you get the same thing, at least at 3 decimal places. And that's what we were after anyway. So it's pretty reasonable to guess now from these data that the local maximum occurs near 0.860. And this is an answer that we get accurate to 3 decimal places. Of course, if we wanted more decimal places, then we would just carry more. But for now, this is our answer. Okay, that's all for now.